Thank you so much. Thank you for coming out tonight. I just so much appreciate it. And I'd like to tell you a little bit about my personal journey in the area of nanoscience and nanotechnology. This July actually is my 30th anniversary since I joined the faculty at Berkeley, and I started working on some of the things I'll tell you about today about 3 years before that. So it's a third of a century of story. And so there'll be an important personal dimension to it. And what I want to tell you about in that more personal aspect of it is the struggles that I've been through over that period of time to find a balance between wanting to work on fundamental discovery and wanting those discoveries to have an application. And of course, we all think of those as just one linearly leads to the other. But in fact, they interact with each other in very complicated ways. And they can, that desire to want to see really fundamental science can lead to a dead end with regard to technology. Or technology, a desire to contribute to technology can lead you astray with respect to doing something important in science. So it's not trivial, actually, to try to find your balance between those. And so I'm going to just kind of relate to you some of my story about that. And I will also try to, sorry, let me get this back to the beginning. And I will also try to tell you a little bit about the most recent work that we've been doing in about the last 5 years that concerns ideas related to energy and nanoscience, as well as some of our failures regarding energy and nanoscience. I think it's good to have those things all balanced out and talk about them. So, the core of what we'll talk about is the study of so-called quantum dots, which are very small crystals. The crystal that you see in the center there is a single crystal of a semiconductor material, and you can see these kind of alternating dots along there. Those represent columns of atoms, so you can count the number of columns of atoms as you move across that, so you can make a pretty good guess. There are, several hundreds of atoms, maybe a couple of thousand inside there. It's a pretty small crystal. And so this journey is about trying to study those materials and the applications that they have found, as well as the applications where they haven't yet found their real home, and we're still struggling to find it. And I'll start the journey by telling you about how I left Berkeley many years ago, 33 now, to go off to Bell Laboratories to spend some time as a postdoc. And when I arrived there, there was this amazing configuration. It was a giant building full of physicists, chemists, mathematicians, everybody thinking about information technology that we all know today. And to get to my little corner where I was living with my postdoc mentor, Louis Bruce, I had to pass through 8 long corridors of semiconductor manufacturing equipment. And all of it was this giant, there were these giant sets of hardware in which you would have very, very precise control of the environment in order to deposit precise positions and layers of atoms. And the project that I had with my postdoctoral advisor that we chose together was to try to see if we could grow in a liquid vat, a small liquid bottle, if we could grow semiconductor materials the same way we might make an ordinary chemical, a piece of plastic, a polymer, something like that, just in an ordinary flask, if we could make such a material. So we were early on in doing this, and we had some of our first little particles. Basically, we would grow tiny particles inside there by supersaturating a solution. And I took the first semiconductor materials that we had to a very, very prominent physicist there at the time, who was kind of the guru of all semiconductor material growth and physics. And I said, see, we grew these materials, they're very exciting. And I was all enthusiastic about it, and he said, well, that's very nice, but you seem like a nice young man, and I think you're poised for a disaster, because the material you're making inside this liquid is bound to be full of all kinds of impurities. Look at all the effort people go to make sure the environment is utterly pristine, and you just have this flask that you're growing things out in the open. There's no way that this can be pure material. So there we were. That was our first challenge, the first instance where our desire to see something, to make something practical happen, in this case, to learn how to fabricate a semiconductor by a very low-tech means, that's really inspired by a technology desire. Well, it didn't seem like that was possible. And so then the question became, well, why not? And so I'm going to tell you a little story about why not, and I'll explain why actually it turns out it works just fine in the end, and how a piece of science came in to, and how a challenge from a technology topic brought in a piece of science that was, to me, unexpected at the time. So it raised the question. The gentleman said, well, you're not going to be able to grow a high-quality material. So the question is, what happens as you make things different sizes? And at the heart of nanoscience are what are called scaling laws. These are rules which would say, if I take a piece of material and I cut it in two, will the properties change or not? You'll recognize that as how Democritus, in his own mind, had imagined atoms being discovered. You keep dividing something in two, take a piece of gold, you cut it in two, you do that over and over and over again. Democritus imagined at some point you'd cut that down to the indivisible. That's what atom means, actually, is indivisible. So the question is, for nanoscience, if I have 500 atoms on the side, or 200, or 100, or 20, will any property change or not? And so here are two scaling laws, two very fundamental scaling laws that help us explain why, in fact, it's possible to make a very high-quality material under conditions you might not have expected, i.e. in this not very pure flask of liquid. And the answer is twofold. The first one concerns the melting temperature. So now, you're going to know a scaling law when you hear, you're going to know two scaling laws when you leave here, and a third one you'll at least think about. So the two I'm pretty sure you'll know are melting temperature and whether there will be defects inside there. So let's just do the melting temperature first. So if I have a tiny crystal, it will melt at a much lower temperature than the normal solid. You can see that here. This is the melting temperature as a function of the size of crystals, which we subsequently measured after this person told us that we couldn't do what we wanted to. So we went back and tried to understand, well, is that true? Could we or couldn't we? And one of the first things we had to think about is, what about the melting temperature? So here's what happens. Imagine that the two of you link arms and people want to pull you apart. Okay. Now imagine that this whole group of people here start making a network of people all holding arms in random directions, okay? It's going to be a lot harder to pull somebody out because you're all holding on to each other. That's what happens in crystals. Each atom is holding on to the one next to it. If they are all holding on to each other, they get to be much more locked in than if there's just a very small number doing that. And so there's a scaling law. It goes like the surface to volume ratio. So the melting temperature actually drops like a rock as you go to much smaller sizes. Why is that important? It's important because it means that we can take a material which ordinarily has to be grown at very high temperature, and we can grow it inside a boiling liquid. It's really important if you want to scale things up to be able to do that. Now, the second scaling law I want to teach you about really quick concerns defects. After this, we're going to go a lot quicker, but these are the two foundations you need, okay? So the second one concerns defects. So from the looks of it, I would guess most of you have at some point been to the jewelry store to buy a diamond for somebody you care for greatly. And in all probability, you were confronted with the classic conundrum, which is you'd like to buy one twice as big, but when they're twice as big, they cost 4 times as much. Which means pretty quickly, you end up finding the size you're going to buy, and that's the end of the story. Okay? Why is that? Why is it that the price scales, like the square of the size of the diamond? Well, you can imagine it has to do with the rarity of the diamond, right? It has to do with how rare the diamond is. Why is it hard to get a high-quality diamond that's large? Well, imagine there's a defect stuck in the middle of growing that crystal. There's a defect someplace inside in the middle, and it's got to go away. It's going to take time. So the bigger the diamond, the longer it will take, and it turns out that scaling will go almost exponentially with the volume. So that's why. Okay, here's the good news for us. We're going to take that upside down. Since we're not trying to grow a giant crystal, we're trying to grow a tiny one, we actually don't need a long time to push all the defects out that might get trapped otherwise inside there. So it's the combination of these two, the low melting temperature and the fact that little crystals actually spontaneously will push out defects to the surface, that means that we can just take a very simple process actually and grow a very high quality crystal in a short period of time and at a relatively low cost. And that turns out to be the case. So that's, there are people making crystals by that mechanism right nearby here at the many ton scale all the time. So it's quite possible to do. So those are your two main scaling laws, and now the third one that comes into this actually will concern one additional property. It's a slightly more obscure one in some ways, although I think I can make it plausibly intuitive for you, and that concerns what we'll call the quantum size effect. So we have a semiconductor material, and what happens in a semiconductor is, depending on the conditions, we've got a charge like an electron that we can make move around, and maybe you can have a gate and have it be switched on and off and so on. And as long as it's a macroscopic semiconductor, that's the end of the story, more or less. But when it gets to be very, very, very tiny, you have to account for the fact that that electron actually has an intrinsic quantum mechanical wave-like property. Okay? It is a wave. And now we're starting to make the boundaries of the crystal comparable to the wavelength of that electron. What's an example of something you might get an intuitive feel from? You've probably been to those museums where you have a ball that ends up in one of those cones that kind of finds its way down into one of those holes down in the center, and it gets faster and faster as it goes down in. Basically what's happening is that as that ball is confined to a smaller area, the kinetic energy increases, the speed increases. Well, that's what happens to an electron that's confined inside a tiny semiconductor. It starts to move really fast. So if I want to create an electron inside a semiconductor, if I want to add one in, I have to pay that extra energy of having it move around fast inside there, and that's called the quantum size effect. And what it means is that the color of the semiconductor, or its band gap, as you can kind of see here, depends critically on the size of the crystal. So the smaller the crystal, the higher the band gap, the bluer the color, if you like, that it will absorb and emit. And that's a very, very strong effect. So it means you can take the exact same material and you can make it absorb and emit light of many different colors. Sorry. Now, there's two other really important things that turned out to be important for us. The first application of these materials that I'll tell you about was taking tiny crystals. They're pretty small. They're the size of a protein, so they can easily go inside a biological specimen. So the first application that is commercial today, was referred to earlier, is actually used very frequently for providing colors to label cells. For example, if you're unfortunate enough to have a biopsy, it's quite possible, most likely, that the pathologist will stain that with quantum dots in order to make the colors, in order to see what's going on there. So these materials are frequently used in that way. And we'll talk a little bit about that as we go along. So here you can see an early example of that. These are the first example. So this is, some years later you'll notice, this work started in 1986 approximately when I was at Bell Labs. I joined the faculty at Berkeley in '88. So 10 years later, we did our first experiment where we had made these little semiconductor materials well enough that and with enough practice that we could localize them inside different parts of a biological cell and then stain the cell. And very quickly, those found their applications into a commercial world, which uses those for biological labeling. Why do they want to use those for biological labeling? Why not just use the same organic dye molecules that people have been using for a very, very long time? Why not just use a dye? Well, probably most of you have had, if you've come to Berkeley, maybe you succumbed and bought one of those tie-dye t-shirts. And if it was long enough ago and you left it out in the sun, it's now completely faded. Okay, that's because those molecules can fade very easily. Why is it that they fade? Well, I want you to think about it like this. I have my little semiconductor. I've cooked it up by growing a small crystal. It was at a very low temperature compared to normal. It's in a big vat. The defects all pushed out. It's a very small size, so I've got the color I want. Everything's okay. Now what? How do I use it? Well, I'll come in with high energy light, excite an electron, and then that electron will now relax back and emit light back out. Okay? That's how it gets used. So now, imagine you're doing that over and over and over again. You come in, you knock an electron up to be high energy, falls back and emits light. And imagine you're doing that in a small molecule or in this nanocrystal. Now when you do that, you excite that electron, it's a little bit like breaking one bond. So again, let's go back to the idea. Imagine that in the first two rows here, you're all holding hands. And one of you raises your hand, that's the excited electron, and it's kind of moving around between you, and then it falls back down again, okay? And you do that over and over and over and over again, okay? Every so often, the person raises up their hand, they get a little too enthusiastic, and they fall backwards, and the chain is broken, okay? It's kind of like that. If you're exciting a small group of atoms with photons, you're putting in energy in there. You do that over and over and over again. Every so often, there's a chance that that excited molecule will react and fall apart. Now, when it's a nanocrystal, a much larger crystal that you can see here, it's got, let's say, a few thousand atoms in it. The chances of it falling apart that way are much less. And so it doesn't bleach. It can just last. There are experiments that people have done to track what happens, for example, when you grow a culture of let's say breast cells to form a little prototypical breast-like tissue, and you can track it for enough months, good chunk of a year, to follow and see what happens, at what point it might, for example, be invaded or have other effects occur, biological effects that take weeks, months, or years to occur. These things won't bleach during that time. So there's a big strength to them in that regard, compared to a dye molecule that will bleach out often in seconds. So that's why they found a lot of commercial use. Now, there's one more piece of the puzzle. It's a technical piece that's important to know, because when we try to find energy applications, my first big mistake was not fully thinking about what I'm about to tell you about. Even though I knew it full well, I didn't lock in on it. So we'll tell you about that. So we've got this little crystal, and we confine an electron inside here, and it bounces around, and that's what it's doing until it emits the light. Okay, so that's the quantum size effect. It's called a quantum dot, because that dot is a box that holds the electron inside, and if you make the box smaller, you're kind of squeezing that electron, you're changing its energy level. But there's one problem with it, which is the edge of the dot contains atoms that are not attached to anybody else on the other side. And it turns out those can act as little sites where a charge can get trapped. It can just go and sit there, and it's lost. Okay? Eventually, it will just return to heat. It will, instead of emitting light, it will return the energy that you put into it down to just making the system hot. So it's a loss mechanism that we don't want. And scientists have solved that for many years by taking one semiconductor material and then growing all the way around it another material that has a larger set of energy levels. So if you like, it's like making a wall. Build a wall around that box that's even taller, and those charges just can't get out. But someplace the wall must end. And so there they are, way out there, but too far out for the electron to ever get there, as long as I'm only interrogating this with light. Okay? So that's the core shell quantum dot. Once we had those working in this biological application, then it was really, the next step was really to think about whether these things could have a larger scale application. The biological one requires the production of minute amounts, all of which can be used in a very effective way. But it was always a dream of ours to see if we couldn't scale this to a technology that would be, you know, a consumer kind of technology at a larger scale. And televisions are what have emerged from that discussion over a long period of time. And so, for example, if you take one small quantum dot that emits green light and a larger one that emits red light, you can disperse them inside a piece of plastic film, and then that can be excited with blue light. The blue light will excite the green and red quantum dots, and they'll make the green and red colors of a television set. And in fact, that does work quite well. And so if, for example, you were looking at Amazon Prime Day the other day, they had some deals on what are called QLED TVs, QLED, quantum dot LEDs, or for quantum dot TVs, you might have seen some. I'm always torn when I see that because I can't decide if it's good that they're being discounted or if it's good that they're just on the market. But anyway, there they are, and they're being sold. And that's a good thing, I suppose. And so, you know, if you go and look at a Samsung QLED or SUHD TV, for example, in the marketplace today, it'll be a quantum dot TV. And you can see some old numbers here. In 2015, there were maybe 25 tons of quantum dots being placed into televisions. Today, it's a lot more. Why are these useful in a TV? Well, this is the reason why. Remember I told you that if I have an organic dye molecule and I essentially break a bond in it when I excite an electron, then it'll relax back. It turns out that when I do that, in a small molecule, I've put this extra energy into it, all the bonds actually change a little bit. They all change their length, their angles a tiny bit, okay? So if you like, when that energy gets put into a small molecule, the molecule changes its shape and everything else about it. And then when it comes back down again, it changes its shape again. And that has the effect, it turns out, of changing how broad, how many different wavelengths of light that molecule will emit. Makes it a broader emission line. Now, you know, for example, when you see light, these colors, if you can see colors, and the ones that you see around you, you're really detecting 3 wavelengths of light, a green, a red, and a blue, right? So you're seeing 3 individual wavelengths. And then your brain is recombining those and saying, ah, that's the color purple, or that's the color, whatever color you're looking at, is by recombining those 3 fundamental colors. So what you need, if you want to make a good display, is for those 3 colors to be very precisely defined and to very closely match where your eye sees things, the colors that your eye picks up. And so there are these funny diagrams that scientists make called CIE diagrams, which show the green, red, and blues that your eye actually detects. And you want to have a device that gets as close to those corners as possible, and where each element is very, very narrow, then you can fill in the entire space of all the colors that are possible. And it turns out quantum dot TVs, because of the large size of the crystal, they have no shape change when they get excited like that. The color is very particular, very precise. It can be tuned very precisely, so you can get a really precisely defined color to put inside your TV, and that's what they do well. So, you might be feeling good about this and saying, oh, this is terrific. Not too long ago, I was with my spouse, and we went to Hong Kong for a science meeting. And if you've ever been there, this is from the Kowloon side, and this isn't a great photo, but it's what I happened to snap with my phone. And there we are, and I notice, oh my gosh, look at it, there it is, SUHD TV quantum dot. It says right up there all the way across, and I'm like, hey, you know, this is pretty cool. There's quantum dots. But my spouse always makes sure to make the picture more complete and points out, well, right there, why does it say LG OLED TV right over there, you know? And there's a reason why, and that's because these organic light-emitting diodes are a really excellent technology. You've probably encountered OLEDs. And so the quantum dot and OLED technologies are kind of out there in the marketplace trying to make the two different versions of how to make colors. And so they do some wonderful things that are excellent. The quantum dot TVs can have, you know, as I was emphasizing to you, kind of a higher color purity, but the OLED TVs have ways of catching up with that in their own way. So there's kind of a marketplace fight going on, and that can be very stressful if you get too much into it. Of course, if you're a professor, you can just take refuge back in your laboratory, or if you're like me, you can just go and take photos and be very happy. And just remember that quantum dots are good because they show all the colors that we know how to make. Now, I'm going to shift gear for the remainder of the time and tell you about the next step of this journey, which corresponds trying to find a use in renewable energy. And I will tell you about a flop, and then I'll tell you about how we're trying to recover from that flop so that we've covered the various kinds of options that can occur. So, in the early 2000s, around the time that the display work was really starting to crank up in the laboratory, we also, of course, knew that we would love to have some impact in solar energy. And the question was, could we take these very inexpensive, very high quality semiconductors and use them to make a photovoltaic, you know, a material that light is incident on, and you collect electricity from it? I mean, why shouldn't we be able to do that? And so we went off trying to do that, and we went through over a period, I'd say, oh, maybe 7, 8 years, of a whole bunch of different versions of these, where we would take our quantum dots, and for example, in this case, we kind of disperse them inside a plastic, and they make a network, and you could excite them, and the charges would move out. And we did other versions where we simply took them, and they were a perfect array of quantum dots with no polymer plastic kind of mixed in, a whole bunch of different ones. And indeed, we did make solar cells. And they were okay solar cells, you know, they were okay solar cells. And at the time, if you recall, it's almost hard to remember, but at the time when we were first starting in this, silicon solar cells were about $20 a watt. And most people estimated that if it didn't get below $1 a watt, there was really no chance for it to become market competitive. And so we thought, well, we got a whole factor of 20 here in cost, so performance isn't really the issue here. What we just really need to do is make something that's really low cost, and everything will be okay. So we tried to do that. We jumped in and we made a bunch of solar cells. They weren't great in performance, but they were adequate, and they were very low cost. But of course, you probably know what happened in that story, which is the silicon technology went on a very fast growth curve, and it crushed us, and that was the end of that. So that causes a period of introspection, you know, when you're trying to make something work for a while, and you think you've got it figured out, and then it turns out that it's not that way. So, you know, there was one thing to think about, which was, you know, whether the choice was good in the first place, and things in terms of the field to work in and so on. But then, you know, another choice around, did we just make a mistake because we didn't think about the problem deeply enough from a strictly science point of view? And I think that that's true, actually. We didn't. And in retrospect, you can, I sort of revealed it to you earlier. If I have a group of quantum dots that are all in an array like this, and I want charges to hop from one to the next, I mean, actually, it's not such a crazy idea, because I told you those electrons have been pushed into this box, and they want to get out. That's why they're zinging around in there like that. They're trying to actually tunnel, if you like, quantum. One could tunnel from one to the next, and so on. And you might make a decent device that way, but the problem is you got to pass through that surface. And even if it's a core shell dot, then the outer surface of the shell has a surface where a charge can get stuck. And so that's just a problem, and nobody's quite solved it, and it's a hard problem. And so now the question became, okay, maybe that wasn't the good idea yet, so is there some way we can get back into this? And of course, it's one of the terrible things if it happened. I mean, it did happen to me in my case, for instance. I had graduate students and postdocs who were working on these ideas of making photovoltaic solar cells, electrically. And at some point, I became convinced that this was not the way we should be going. So now we had this kind of dissonant moment because there's a gap here. What are we going to do, And of course, they felt it very keenly. But eventually, an answer did emerge, and I'd like to tell you about it. And it's a very strange answer. It's not something you might at first guess, and it's taking us into very bizarre directions that I never would have guessed. But what it involved doing was first just going back and looking at the little quantum dots and thinking, what do these things actually do? And the answer is they absorb and emit light really well. They're actually champions at absorbing and emitting light. So why don't we stick with that and think about that idea? Okay, so I'm going to tell you now about what's called a luminescent concentrator. It'll take about 5 minutes, and then we'll see how that leads to other things, and then we'll wrap it up and have lots of time for questions. So here's the idea. Have you ever seen photographs, or maybe you've actually seen in person, that sometimes there'll be solar cells, often out in remote places, where there's a giant parabolic dish that focuses down onto the solar cell? Okay? So it takes the light from a great big area, and it focuses down onto that little solar cell. Why do they do that? There's 2 reasons, 3 at least. Okay. One of them is because you don't want to have to build a solar cell. It's a lot cheaper to make the reflector than it is to make the solar cell. So you save some money. The second is, it turns out that when you really concentrate the light, and it becomes very intense, and I'll explain this to you a little bit more in a minute, when the light gets really intense inside the solar cell, its electrical performance actually improves. It actually generates more voltage when it's being illuminated from with 500 suns than when it's being illuminated with just 1 sun. So the actual performance of that little piece of solar cell is higher when it's illuminated that way than it is when it is just an ordinary equivalent large area solar cell, which then also costs more. So there's been this idea out there for the longest time to make what's called a luminescent concentrator. What would this be? Remember that plastic film I showed you with the TV kind of thing in it? It's kind of like that. It's a plastic film, and inside it is a material that absorbs light and then shifts it to another wavelength a little bit, becomes a little bit higher energy, and then the light reflects around inside that plastic. So if you looked at this like a sheet of plexiglass, it's like having a sheet of plexiglass with something inside it that just glows when the sunlight hits it. And if you look at the edges, it looks very bright all around the edges. Okay? That's a luminescent concentrator, which works by taking the sunlight that's incident on it and shifting, say, the green light to red, and the red light will bounce around and then come and now taped to the edge, instead of having this giant parabolic mirror, you just have a big plate, and on the edge of it someplace, you tape a little solar cell, and you put silver tape around the rest, and there you go. That's your luminescent concentrator. So people have tried to do that for a really long time, but it's never quite worked as well as they would like. So now, why should this work at all? Why is this a good idea for a concentrator? I'd like to explain something to you that's not intuitive. It's a very tricky physicsy concept, but I think it's easy to explain. You see the red dot, right, that I'm moving around, perhaps? Okay. That's the little laser pointer. And the reason you see it is because although the light proceeds in a perfect line from me to that screen, the moment it hits the screen, because the screen is very rough, it sends rays of light out into each one of your eyes. Okay? And that happens. Now, would it ever be the case that all of a sudden the light from each one of your eyes could come all the way backwards? and come back into my laser pointer? The answer is definitely no, and that's because of entropy. When the light's all going in one direction, it's actually a very ordered light beam, but once it's scattered off of that surface, it's now going in many directions. It's actually more disordered, and by the laws of thermodynamics, things will spontaneously become disordered. If you want to order them, you have to pay an energy cost. So in a luminescent concentrator, what you do is you actually send in blue light from all random angles, and then you send out red light at one exact angle. You lose a little bit of energy between those two, but that energy difference is what allows you to concentrate the light very, very, very highly. So it makes, if you like, a little engine. It takes the high energy light from the sun, it lowers its energy, but it sends it all in one exact spot. And that's the trick of a luminescent concentrator. It uses an entropy change in order to organize the light and make it all go in one direction. And that's what it does. And the reason these are so interesting is because, as you probably know, for example, if you live in Berkeley, you really know, lots of days are foggy and cloudy. And so you can't really use one of those big parabolic collectors, because all they will do is image the light from a point source. So if it's a very clear day, it'll take in the desert, it will take the light and then focus it down to a spot. But if it's a day that's not so clear, it can't really do that. And the light is very diffuse, it comes from all angles. The luminescent concentrator can just sit there, collect all that light, and then send it off into a certain direction. So indeed, that's what we do. We make quantum dots as luminescent concentrators. We take this core shell structure I told you about. It's got a large volume shell that absorbs the light and transfers all the energy into the core, and then the core emits the light at a shifted wavelength, and then we can put that into the luminescent concentrator and make a device. Does it work well? Not well enough. So it's in the early stages, this idea, but it uses light in a very particular way. So we've got a project going with friends at different universities, at Caltech, here at Stanford, and at Illinois, and we're trying to build a practical device with this, and jury's out. We're going to find out. Here's one of the things that goes on, though, in such a device. I just want to leave you with this thought. It's a funny thing. If I make a television set with one of my quantum dots, with one of our quantum dots, it will absorb the blue light and emit green and red. And it has to have an efficiency for doing that of about 90% or so. So if 10% of the time it doesn't work great, that's okay, as long as it's 90%. But for the luminescent concentrator, it turns out that in order to get the 500-fold concentration factor that solar requires, it actually has to have an efficiency for every time it absorbs light, that it will also emit it, of 99.99999%. It's a small detail. It turns out that's hard to do. And it's really entertaining to try to do that. So that's what we're doing. For example, we have a good friend here, Alberto Soleo, just up the road here at Stanford, and we can't really go measuring the photons anymore because they're so efficient. So what we do is we actually measure the heat that gets lost, and if we do that carefully, we can kind of figure out, okay, we can make a quantum dot today with 99.7, it's a little bit old now, maybe we can do it 10 times better than that, but we're still not quite there. So the last thing I'll leave you with is kind of this feedback loop. So we've now got a feeling, I mean, we think this is possible to do, the 99.999. I think it actually is possible to do. We don't know. I mean, that's unknown, so we'll have to try to find out. But to do it, we actually have to make our quantum dots. I mean, I told you earlier we could make them essentially perfect. And that was approximately true. But now they have to really be perfect. And so the other half of our activity is trying to figure out, well, can we really, really make them perfect? And so that involves now developing, these movies aren't all playing quite right, but anyway, we have to just sit there now developing new techniques, which we have been doing for a while now, by which we can actually, and I'm not going to go into the detail on it, but we can take our little crystals and place them in a liquid environment where we normally grow them. And as they rotate, we can observe them from every side with an electron microscope. And then we can see every atom. And we can go crystal by crystal and just try to see, are there defects in this thing? Where are they? There shouldn't be too many because the temperature was well chosen, and they're small enough that they should anneal out. But you know, everything matters now, so we've got to make them as really close to perfect as we can. So that's what we're trying to do. Now, what I gave you as an example turns out to be something that can be generalized. And so I'm going to tell you about just a pretty crazy idea about light and energy. And this now is off into the highly speculative. I mean, you know, we should have some period where we just talk about things that are really hard to do, and who knows if they'll happen or not. And so I gave you an example where we said we could have a material that absorbed and emitted light, and in order to have a conversation between one scientist and another, we'd actually have to use a logarithmic unit to say, you know, because we're going to be comparing 99.99% to 99.999%. It's much easier to subtract that from 100 and take the log and say, you know, what have I got there? You know, they're going to differ by that. So it's really a regime where we're down to high levels of perfection. What are we really doing here? Well, it turns out we're using photons to convert energy. If you're familiar with the foundations of energy, our science of energy actually all developed around the science of thermodynamics. The science of thermodynamics developed around heat engines, if you know the history of it. And in fact, it was around the time that the steam engine was really invented that the science of thermodynamics really took off, because people wanted to understand, if I have a gas and I expand and contract it, and I make a piston, how does energy convert? And they wanted to know the laws that concern that. That luminescent concentrator that I talked to you about, it turns out it's a compressor for photons. It's taking light that's coming from all different random places, and it's placing it all to go to one exact spot, all with one exact angle. So if you like, it's the equivalent of taking a gas and compressing it. So it's half of a steam engine, if you like. So now you start to think, well, how come we don't use light, which is a carrier of energy, the same way that gas is a carrier of energy inside there? How come we don't use photons to make engines? Well, people thought about that a long time ago, and the problem is that if you try and do that, the photons escape. They're easy to get out. You know, they have, you know, light is really no mass, and so it's really easy for it to get lost in different kinds of ways. And you just imagine now, I've got my refrigerator at home, and it's sitting there cycling, and an hour later, half the gas in the compressor has gone out. It just doesn't work. So in order to actually make a new set of engines that worked on photons, what you'd have to have actually is a set of materials, both the compressor that I just talked with you about, as well as others, that operate with very low losses. And it turns out the field of nanoscience, just like I told you the scaling laws for the melting and for defects and things like that, it turns out the scaling laws help us understand that if we make very small materials, we can make them very close to certain limits where it's possible in a practical way potentially to make those good enough that we could start to use light in that way. So here are 3 examples of technologies that would be equivalents. Have any of you heard of the Starshot project? I'd recommend that Café Scientifique have somebody from the Starshot team come and talk with you sometime about it. The idea is that you would have a little tiny miniature spacecraft. The actual business end of it would be, you know, way, you know, 10 microns, 100 microns on a side, a little cube, but it would be attached to what's called a light sail. The light sail would be several meters squared reflector. And then from the Earth, you could use a laser to excite, to drive that light sail. the photons would reflect off of it. That would impart momentum to the light sail, and it would move. So that would be an example of light. Another one would be a refrigerator. I told you about the compressor, and so on. So you can imagine there could be a whole set of different ones of these. I'm going to drop it there and just say that this is where our little journey into producing and detecting light has led us. And it's been a journey where trying to understand an early technology challenge posed science challenges. And then the science challenges led us to possible new applications we hadn't thought of. And that's been a very productive loop, but also one where you make your share of mistakes, and you have to just kind of accept that and then say, okay, I'm going to try again. So thank you for your attention.
Thank you, Paul. We now have time for questions, and as usual, I will just approach you so that everyone can hear your question. So I'd like you to wait until I'm there. And there's the first question already.
So this has absolutely no medical applications to it, or does it?
Which one? So the dots themselves are used medically in imaging experiments. Not these particular kinds of dots that I've been involved in have been used for biological imaging for research, and also in medical diagnostics and, say, pathology samples and things like that, but not in human therapies. There are people who try and do that, and there's a whole, subfield that works really hard on that. It's got its ups and downs, and I didn't really talk about that. It's a complicated topic that, I didn't really go into. But they're not, the ones I talked about are really are used extensively biologically in those two contexts.
I just wanted to know if your field is at all related to thermoelectrics and the search for superconductive materials for energy.
Yeah. So, if you look at, I didn't really, the field of nanoscience can certainly try, and there are many people working in it trying to make better thermoelectric materials. As you probably know, in a thermoelectric, what you would like to do is have very, very different electrical and thermal conductivities. You'd like to have a material which can conduct, let's say, electricity extremely well, but heat very poorly, or vice versa in some way. Normally, there's a kind of fixed ratio between the electrical and thermal conductivity, because when electrons move through an object, every so often they'll bang into an atom, and that'll cause heat. And so the electrical and thermal conductivities are kind of linked to each other normally. So it's definitely true that in the field of nanoscience, it's possible to make some materials which will have very, very unusual ratios of electrical and thermal conductivity, and many people have tried consequently to use those to make practical thermoelectrics. We have not worked on that in my research group. In the last example I was showing, I didn't go over it, but there was a version of a sort of essentially using photons to mediate and make a thermoelectric of a very different kind. So there is a possibility, of course, to make what looks like a kind of thermoelectric with this photon-based idea, but I got the feeling I was pressing my luck on explaining too many of these different things, and so I just skipped over it, but we could certainly tell you about it, yeah. It's a long shot for us to ever be involved in a thermoelectric, but the field of nanoscience, it's a big topic, yeah.
How reliable are quantum dots? How long do they last, and what do you do with them once they stop working? Do you recycle?
How long do quantum dots last? Well, of course it depends. So if they're, for example, embedded inside a display, they last for as long as you want to keep that display, and you can pull out the polymer film subsequently and then harvest the materials from it. It's possible to take So the quantum dots in the right chemical environment will last indefinitely, but it's possible to create very easily a kind of chemical environment in which the quantum dot will come apart in thousandths of a second. I mean, just instantly from the point of view of anything that you could see. And of course, then you can harvest all the things that it comes from, if that's what you want to do. I gather probably implicit is, how are people going to dispose of them? I mean, and that's a really big question. So these materials have pretty well-defined protocols for how they can be taken apart and recycled if people choose to do that. To the extent that that's happening in the world is a very complicated subject. I do want to say on that front, though, it's not a topic people explore a lot, but I honestly do believe that making objects out of nanomaterials has the possibility of being able to join them together and then take them apart, but keep the particle whole and then reuse it again. And just at one level, think of it like this. Most of the materials that have high performance that we use today are very complex composites. They have many different things inside them. And the only things we recycle really well tend to be very pure elements. I'm going to tell you a horror story about that I think about every day, and I don't know what to say about it. Do you know one of the main ways of recycling these is to take apart the glass and the casing and take the circuit board. I'm not kidding. It's done in other parts of the world. You won't find this in the United States, but they'll take the circuit board and burn it. And the heat from burning the plastic is used to distill the metals, which can then be collected as pure metals, and it's cheaper than mining. So, I mean, if you wanted to ask for what's a grand challenge, it is to try to make materials which can have the high functionality that come from these very intricate combinations of materials, but to be able, under the right chemical conditions, to take them apart into pieces that you can then reuse. That seems to me like it's a really important agenda. Unfortunately, it doesn't get the kind of traction that it needs to get, I think, to really become a science movement in the way I'd like to see it happen. Yeah.
A couple of related questions. The first one, when you talked about the 99.7, but needing to go to 99.9s, is there a simple way you can explain why at 99.7 it doesn't work? I mean, why you need to go to that level? And I guess the second, a related question, when you talked about that sail, that star shot, when you do get further, couldn't you have like a space station which doesn't need the beam of light but collects the rays and then uses that and converts it up there?
Okay, so for the 99.7 versus 99.9, think of it like that compressor I was telling you about. That if the compressor has any leak in it and the gas gets out, then it stops being able to compress well. And it turns out in that luminescent concentrator, you're trying to collect all the sunlight. And to get to a concentration factor of 500, the light has to bounce around inside there huge numbers of times. And that means it's getting absorbed and emitted and absorbed and emitted a huge number of times by the quantum dots. So one quantum dot will get cycled huge numbers of times before it actually sends the light to the final detector. And for that reason, it can't have any, so in the display, it only absorbs light and emits a couple of times. So if it has a little bit of loss, it just doesn't matter at all. But in this concentrator case, that dot has to do its job, many, many, many times before, and that's why it has to be so darn efficient. In some ways, we're happy about that because it gives us a challenge to try and make a much better dot. But there you go. I mean, that's the reason why. The Starshot project is a beautiful one, and it deserves its own kind of session with folks here. But the idea is that you would illuminate the sail for several minutes, and then it can be accelerated to a quarter of the speed of light. And then it's in a frictionless environment, so it would go, in this case, Starshot, meaning to go to another star. You could imagine other versions of this where you explored other planets, all kinds of things that you might do. But the idea is basically to have concentrated all the fuel. If you like, all the fuel is really sitting on the Earth, and then photons are sending the energy, so you don't have to lift the fuel up into space in order to propel the spacecraft. Now, the consequence, though, is the total mass of the spacecraft is teeny tiny. So it's not like it's not like a spacecraft that's going to take people somewhere. It's just going to take an electromagnetic probe someplace, which would then send a signal back. Yeah.
Thank you for a great talk, right? So I had a quick question. So in the quantum dots that you were showing, right, there were CDSE, cadmium selenide, and telluride. And for some reason, they always keep coming up, right? So why are those quantum dots?
Okay, let me talk to that. So the first materials that we got really good at making were cadmium selenide and the related materials. It turns out today, for example, in those displays and so on, that's not the material that's used. They'd most often be indium phosphide. There are many other materials that are used that are similar. So there's probably about 20 materials that have been made as quantum dots in very high quality. Some better than others, but high enough quality that they can be used in these contexts. So that's the material I'm showing because it's kind of the one that all the practice was done in and where the principles were elucidated ultimately, but it turns out many of the same rules will apply to lots of materials, not all, but lots of materials. Yeah.
I guess the second question I had, not a technical question. I mean, you spoke about the push and pull between science and technology for you. Which side are you on right now?
I refuse to pick sides, but I suppose you could say that I did pick sides because I stayed in the university my whole career, and I belong in a university, definitely, not in a company. I would be an absolute disaster in the real world of companies. So that's not where I belong. But I'm fascinated about the interplay between those two, and I tried to indicate how much. Going back to that one example, I think it's really, I didn't talk enough perhaps about the example where we failed, but if there's one thing I learned, for example, it's that if you're trying to develop a new technology via science, you have to actually do more than just have something that potentially is less costly. If there's one lesson I got out of that, it's that there has to be a new foundational concept that underlies it, that distinguishes it unambiguously in performance and quality from any other potential or incumbent technology. That's a goal one should have. And it turns out that really puts a high premium on the science up front, and it forces you also in the technology discussion to be a little bit more self-critical. One of the dangers that we face is, I made this quantum dot, I want to use it, I've got my hammer, of course it's a nail. And it turns out one of the nice things about the technology world is it does not forgive you. If you're taking a hammer and pounding your finger, it hurts. So it's a good feedback loop. Oh,
hi there.
Sorry.
In the data storage world, there's been some research in using indium arsenide and stuff to sort of model after the DRAM model. Charge it up, it goes down. If you turn it off,
park
it
a
goes
charge
away.
in it, yeah.
Are you aware of research that uses any quantum dots to establish persistence, like the flash? We use quantum tunneling in the flash.
People have worked on that a lot. I'm not sure where it all stands today, but there's a lot of work that has been done over the years where, so what you can do is have a film of quantum dots sandwiched between electrodes, and you can, addressably, and you can bias it to put charges in there and then remove the bias, and they'll just sit there for a long time. Question is how long, which is your question, and so there's a lot of work that's been done on making memories in that way, and I used to track that subject a lot about 10 years ago, and I haven't recently, and I don't know. So in principle, really what it's all about is the tricks you would have to employ so that at that higher bias the charging is facile, but then when no bias is there, the charge will live a really long time. So you have to kind of engineer the barriers between the dot and the electrodes to a high degree. And it doesn't seem to me like that's something that couldn't be done. And I know people have tried a lot. There have been several companies that launched off into trying to do that in different ways. I don't know the status of it, but it's not out of the question that one can do it. I should also just say there's another set of scaling laws we did not talk about concerning what happens to fundamental magnetism that are very related to the scaling laws I talked to you about regarding defects and things like that. And there's a critical size of little magnetic particle that is kind of a perfect size for making a memory out of. And depending on the material, it might be 7 or 20 nanometers in size, something like that. And people do a lot of work to make magnetic memory out of those kinds of crystals. It's a whole thing.
So, if you look at the Berkeley rooftop solar panel, which doesn't have a parabolic reflector, and then you look at maybe a corporate parking lot set of solar panels that maybe could have a concentrator, also in Berkeley, but that concentrator doesn't work very well. And then you look at the concentrator out in the desert with vast acres of solar panels, multiple concentrators probably. So when you look at the 97% versus 99%, could you use the quantum concentrator in the cloudy environment and not have to be as efficient as you would to compete with the reflector in the desert?
Yeah, it's a possibility. You are correct. It's a question of... So here's what's interesting. It's a very tricky, this is where it gets very tricky, and you have to really think about markets well. Homes have a very finite area in the roof. So what's good enough efficiency? What's the break-off on cost that people will tolerate? All kinds of things like that. But you're certainly right that could be true. The project that I did show very briefly, I didn't go into any detail on it, that we are working on with our colleagues here at Stanford and Caltech, we got a little collaboration going, is in fact to put an extra coating on top of a silicon solar cell, which will make the cell, if everything works out as we hope it will, we're kind of in the midst of assembling these now. In principle, we should get to a 32% efficiency silicon solar cell, which typically the ones you'd buy in the store today might be 19-20%. There are some that are in the sort of 23-24%. If you can add this layer on top and bring it to 32%, and the cost that you've added on top isn't too great, maybe that's an opening. Unclear, but maybe. So that's one possibility. It turns out once you start thinking about these concentrators, though, you're on the right track, because it turns out there may be several openings for how to use concentrators that don't look just like the conventional solar cell. There may be a whole bunch of those. And so that's a process that we're in, that having a lot of discussions about. Maybe it isn't a straight simple solar play. Maybe it's part of something else, and that's a good discussion to have.
Thank you very much. And now I want to ask the question about nanostructure. In nanoparticle material, easy to aggregate, but your structure is stabilized in nanostructure. What happened? Is there a secret or some reason?
Is there a secret to what?
Why your structure is stabilized? Usually, the nanoparticle is easy to aggregate, but your structure is stabilized. Why? Is there any explanation?
So I think as I tried to explain why it is that we can make a very high quality crystal. On the question of stability, actually that is a very interesting question, because depending on the chemical conditions, we can have a nanoparticle be stable for as long as any of us would live and much longer, or come apart before our eye could blink. So they're their chemical stability depends on the environment that they're in very much. And so the trick is all about making sure that you've controlled the environment all the way from when they are first fabricated to when they are embedded into a useful device. And then, of course, the question was what happens after that? And we had a little discussion about recycling. That is, another question. But that's what I want to emphasize is that there are circumstances where you can take a nanoparticle apart unbelievably fast. So it's not like they are. Let me put it let me be even more careful. A nanoparticle is not an equilibrium state of matter. It's a very high energy, not equilibrium state of matter that you can keep and use if you think carefully about it. But the moment you don't protect it, it returns back to conventional material immediately.